So this is the first sample of our practice. As you can see here, this is the layer of carbon that is formed in this sample, and now we're gonna measure the in the beaker's hardness machine.
At this layer, we can see that the hardness of the beakers is 420 HV. Let's see of the next point. What is it?
This is the second test that we made in the first sample. As you can see here, the hardness that we have in the middle of the layer between the carbonized part and the normal part is of 476.
As a reference from the first test, we can see that the hardness increases for like 50 units, like 59 units.
In this test, we can show that the hardness is decreasing.
I have the theory that if you go to the center of the piece, you are going to decrease the hardness.
In this case, we are going to analyze the second sample. So here we have the carbon layer of the second sample, and here in this part, we're going to make the first hardness test. We have this result. So in this case, in the second sample, we have a hardness test of 295.
We can see in this layer, in this sample, we can say that the hardness decreases. So we can say the other theory that if you go deeper to the center of the sample, you are going to have less hardness. Here in the third sample of the third test, we have a hardness of 317. It makes us think in our hypothesis.
In this case, we make a hardness test in the carbon layer of this sample, and as you can see here, in comparison with the other sample that we made in the other test, this gave us 326 in hardness. So it has an increase in hardness in comparison to the one that we did in the middle of the layers. This is our third and final sample, and we have the first beaker's test applied to the sample. As you can see here, we have the first carbon layer, and then the material, the rest of the material, and here we got 290 in hardness test.
Here in the third sample of the third test, we have a hardness of 317. It makes us.
Right now we're making the beaker's test for the pure sample of our alloy that is steel 4140. So as you can see, after making the test, we got a result of a hardness of 311 for the pure sample, and here is the result of our experiment.
Carburizing is a heat treatment where we diffuse carbon into a steel to increase its toughness on the surface. Then we have the carbon equivalent, that is the empiric weight percent of carbon in the steel. Then we have a carbon potential in the atmosphere, that is the capability of the atmosphere to provide carbon into our steel. The cemented layer is the portion of our steel that is now carburized and has the carbon that is absorbed. Quench is when you rapidly cool your piece on water or oil to have some properties. Temper is heating the metal below the critical point for some time and they're cooling it in air. And diffusion is the net movement of molecules or atoms from a high concentration to a low concentration area.
So the main applications for the cementation of the metal mechanic industry right now it's obsolete because most of the companies they don't use this kind of process, but still some of the clamps and axles represents this type of process because it needs a superficial layer that has to be resistant to wear, but inside in the nucleus it has to be relatively soft but resistant to the hardness.
First, we put in our diagram the 0.4% of carbon, and we can see that at 900 degrees we only have the white component of the austenite. At 100 degrees we have ferrite plus austenite, and at 200 Celsius, that it will be just like 400 Celsius, we have just the ferrite plus the cemented. Uh, in the microcrystalline, that only happened in the reaction, and in the phases are the state that the matter is in the different points of the graphic at different temperatures.
Now we can see prove our theory in the graph with the different lines that in the first layer we got the in the carbon layer we got the highest value of the hardness test.
So now we're going to talk about the cementation steels, and there are two main cementation steels. The first one is blister steel, and the main characteristic of this is that iron gains 1% of in mass of the charcoal, and after it becomes an heterogeneous bar. And after the second one, or the second main one, is a shear steel, and it's when you have to heat the blister steel, and it has to be sheared into a short length with high heat, as it says here, and after it has to be walled by hammering, and we have to finish with the hammer at the same or higher heat.
Okay, to find the depth of the carbonized layer, we can use the formula that we use in the depth material, where everything is given except the diffusion coefficient and the depth. That is the one that we want to find. We can use this formula to find the depth of the iron as the carbon in iron, and they give us this value, and then we go to the tables and we find this value and we find the z, and then we just clear all to find the x, that is 1.071 times 10 at minus 4 centimeters.
So the main type of cementations are three. The first one is the solid material cauterization, the second one is the rich gas in carbon, and the third one is the liquid cauterization. And most of them have different applications, and one of them are the near finished components, the mild steel pressing. Other one is the heavy duty alloy steels transmission, so they can work from the mild steel until heavy alloy steels, and also it works with road gears and another ones. So the main steels that uses this type of process, the ones that we work in the lab, are the ones that have low carbon, and this represents less than 0.45% of carbon inside the material, and that's the main steels are the ACs 1020, 1022, 3310, 4035, and another ones. So these type of materials are mainly used in the automotive industry, the aeronautical engineering, and also in general the mechanical engineering for most of the uses. For example, the drills and the tools for machinery, and another one.
So it was very interesting for me to discover how this process works. Since we made the Vickers test, I had the chance to visualize how these layers were formed in the material, and this is very useful as a mechanical engineer since it's a heat treatment that is widely used in the industry.
It was interesting to know how the different concentrations of carbon and how the different heat treatment that we apply with different temperatures, times, and cooling methods can change the properties like hardness in our material. And it's good to know that as engineers, so when we need to do some application, we know what procedure to do.
I like this practice because now I can know the heat treatment for achieving the mechanical properties that we want. Not only get satisfied with the mechanical properties of an alloy, and I like all the heat treatment that we use because I've been part of all the process, and I can see all the stages that the process has.
The lab was really useful for me because I understood most of the phase diagrams and the heat treatments that works with the steel, and this one is really easy to use and it's wide used also in the industry, and also the possibilities that it has and the advantage that the material can have if we make this kind of heat treatments, and like there are other possible heat treatments in the industry. So this special lab was really useful for me because I can apply this type of processes in my whole life as an engineer.